and what is the meaning of design. So when we are talking about the term, or we are referring term analysis of a member, analysis of a structure. So basically what is the purpose analysis? So analysis refer to the evaluation or calculation or estimating the capacity of a structural member to resist the effect of various loads or movements to which it may be subjected based on its geometry. That means what is the cross-section dimensions, what is the length, etc., span. So what are the geometry of that particular member, and from which material it is made up of, whether it is of concrete of grade M20, M30, etc., or it is made up of a high strength concrete. So accordingly, based on the geometrical dimensions as well as the material type, material properties, we will be able to analyze that when some particular set of loading is acting on the member, so what will be the effect of those loads, just as movements as well as shear force, etc. So that capacity of the member to resist, whether it is able to resist or not. So all these information we can get by doing the analysis of the structural member or particularly structure. So for analysis you can refer IS code have mentioned some of the guidelines. That means what are the various methods of analysis which you can refer. Now let us briefly discuss about what is the meaning of design, so that we should never get confused in the meaning of the design. So design means working out the depth, breadth, etc. That means to work out what are the dimensions of the cross section of the member, and reinforcement details which we are going to use in case of RCC structure. So reinforcement details for the member to safely and economically resist the external applied load. So purpose of design is, very first is, it is the safety of the structure in throughout its life, as well as when you are going to do the design. So your design must be economical. It should be economical. We can say it must be safe and it should be economical whenever any external loads are acting on it. So this is the difference between the analysis and design. In design part, we are working out the dimensions as well as deciding the material, and in analysis what we are doing, we are checking the capacity. So during the design of any RCC structure, we will be doing some of the calculation related to the design aspect, and some of the calculation we will be doing towards the analysis. So they will be going simultaneously one by one. Now let us understand very clearly and very patiently. So what will be the behavior of the RCC beam under bending, or in more technical language we can say in flexure. Now to understand the behavior of the beam before designing. So before designing we have to understand the behavior, that how it will be behaving when some load will be coming on, or load in the form of, it may be compressive load, or it may be tensile load, and it may be any type of movements, torsional effect, whatever be. So let us consider that a RCC beam, or RC beam you can say, is subjected to transverse loading, and the load is gradually increased in magnitude until the beam fails. So we are assuming for our understanding that there is a RCC beam which is subjected to transverse load, and we are increasing the load gradually in magnitude till the beam member get failed. So how will be the behavior, how the beam section will behave before it's failure. So that we want to understand today. Now whenever any beam is subjected to transverse load, which we are going to increase gradually, so beam will go through very important 3 stages before any type of collapse. So what are these 3 stages that we have to understand it more clearly? Then we can understand the mechanism of the RCC structures. So very first is uncracked concrete stage. You have to keep in mind that concrete is prone to cracks, or concrete may have some porosity. So first of all, when we are taking into consideration any RCC beam section which is subjected to loading, so it will be going through 3 stages before finally it getting collapsed. So very first stage is uncracked concrete stage. We will elaborate in the details. And the second stage is concrete is getting cracked, but in elastic stasis stage. And very third stage is ultimate strength stage. So we have to differentiate all these 3 stages carefully so that we can understand the mechanism how the RCC section will behave. Now let us go one by one. Very first is uncracked concrete stage. Uncracked concrete stage. So definition part or elaboration, at small loads, as we have already told that we are increasing the load gradually. So when the load magnitude is small, so at small loads, when the tensile stresses which are developing in the member are less than the modulus of rupture. Now what is the modulus of rupture? The bending tensile stress at which the concrete actually begin to crack. So when you are increasing the load, what is going to happen? Tensile stresses will be increasing. But till the tensile stresses are less than modulus of rupture, we can say the entire cross section of the beam is resisting the bending with compression on one side and tension on the other side. So what we want to say here that a member is made up of concrete, and as you start applying the loads, what will happen? Some tensile stresses will develop, some compressive stresses will develop. And before reaching the modulus of rupture stage, when your tensile stresses are lesser than modulus of rupture stage, then whole of the cross section of the beam will be resisting the bending effect, and one side compression, that means above the neutral axis. Later on we will discuss the neutral axis, compression on one side and tension on the other side. Now you can refer this diagram carefully. Now here what we have taken a sketch or a diagram, a rectangle member. This is the cross section of a rectangular RCC beam, and this gray portion is it indicates concrete basically, and these circles indicates the reinforcement, steel reinforcement, and this dotted line in the middle of the section is neutral axis. And in the previous lecture we have gone through the details what is the meaning of neutral axis. You can refer if you have any doubt. Now this is the strain diagram. Now how strain occur? Now we are talking about the uncracked concrete stage. So in uncracked concrete stage, epsilon c is the maximum strain in compression, because upper side of the section it is compression, here this portion will be in the tension. So strain here will be compression, compressive strain, and strain below the neutral axis, you can say strain is getting increased with the distance increasing from the neutral axis. And at the topmost fiber there is compressive strain, and the bottommost fiber there will be the epsilon c in tension. So compression as well as tension. So that's why we are we have discussed that entire cross section of beam is resisting bending with compressive stresses on one side and tensile stresses on the other side, and some of the stresses will be taken care of by steel, but they are not prominently considered here. Now, second type of section behavior is cracked concrete in elastic stresses range within the elastic limit. So as the loads we are going to increase, when you increase the load beyond the modulus of rupture, so what will happen? Cracks will begin to develop in the bottom of the beam. Bottom of the beam means below the neutral axis, and the moment developed at these loads, when some load is applied, it will create some movements. So when your load is beyond this limit, modulus of rupture, then the movement which are getting developed at that load, when the tensile stresses in the bottom of the beam equal to the modulus of rupture. So when they have reached modulus of rupture, and it terms as cracking movement. So that movement which is at the level of modulus of rupture, that movement is termed as cracking movement, MCR. Now you can understand it more effectively in this diagram. Now you can see here we have taken a beam, and it is simply supported beam, and some load may be acting from the top. That means transverse load is acting. Accordingly, we have drawn a movement diagram, that is the bending moment diagram. So you can see here at the level of when your movement is reaching up to cracking movement, so within that range you can see some cracks are getting developed. So these cracks are due to this movement. That means these are the flexural type of cracks which you can consider. Now, if you still go on increasing the load, on further increasing the load intensity, the movement will become greater than the cracking movement. So here M will be more than MCR, and then what will happen? Crack will quickly spread up to the concrete surrounding the neutral axis. So now if there is suppose neutral axis, then these cracks will start developing in the upside. That means from the bottommost fiber of the concrete member and towards the, that means cracks will start propagating towards the neutral axis, and the neutral axis begin to move upward. So later on you will be able to understand what is the meaning of this neutral axis movement. So at this time we are able to understand that when you are increasing the load, and accordingly movement will develop, and as soon as the movement reaches to the cracking movement, some cracks will develop at the bottom of the member. That means due to the tensile stresses developed, and further as you increase the load intensity, accordingly the movement value will also increase, and it will cross the cracking movement, and after that the cracks which have started at the bottommost fiber of the beam section, they will start propagating towards the neutral axis. So we will say now the concrete is in the cracked zone. So earlier it was uncracked zone, now it is concrete has started cracking and some cracks are developed. So the concrete is in the cracked zone, and when there are cracks, so we can say that now concrete is unable to resist tensile stresses. So effective concrete section is reduced, which is taking the stresses. That's why we have to provide steel reinforcement so that it can take care of the tensile stresses. Now here I can just create one question for all of you, that as we have discussed, as the movement crosses MCR, then the cracks will start propagating from the bottommost fiber towards the neutral axis, and we are saying that now concrete is in cracked zone, and it will not able to resist the tensile stress. So my question here is very simple: why we are using only steel reinforcement to take care of the tensile stresses? Why not we can use some other material as a reinforcement? Why we are using steel basically as a reinforcement so that it can take care of stresses. Why only steel is chosen? So the stresses now developed will be transferred to the, and beyond this what will happen, the stresses will be transferred to the steel. So steel will start taking the tensile stresses. So here we can just try to conclude that since concrete is weak in tension, so it is assumed that all the tensile stresses will be taken care by steel reinforcement. So after that we will be saying that whatever be the section be above the neutral axis, it will be taking the, it is our assumption, it will be taking the compressive stresses, and whatever be the sectional area below the neutral axis of where concrete is still there, and that will, we will just assume that however it may take some stresses, but we will say that concrete below the neutral axis will not take any tensile stresses, only steel will take care of all the tensile stresses. Now third stage, which is very important, which we want to discuss here, ultimate strength stage. Ultimate strength stage when yielding of tension reinforcement can happen and collapse can occur. So how collapse occur and how ultimate strength reaches, so now we will discuss. Now in continuation to the previous cases where we were increasing the load, now if the load are increased further, then tensile stresses in the reinforcement and the compressive stresses in concrete will further go on increasing, and the stresses over the compression zone will become non-linear. So now we are moving out of linear phase. So compressive stresses, stresses over the compression zone will become non-linear. However, the strain distribution over the cross section is linear. The distribution of stresses in compression zone will have the same shape as of the stress strain curve in case of concrete. So stresses will be distributed and the shape of the stresses in the compression zone will be just similar to the shape of the stress strain curve in case of concrete. Now important point is, at one point particularly, either the steel or concrete, either the steel will reach or concrete will reach or both will reach their respective capacity. Then steel will start to yield, yielding will start, or concrete will crush. So either steel will yield or concrete will crush, or possibilities steel will yield and concrete will crush simultaneously. So when this happens, this is called ultimate stage or stage of collapse. Now you can see this diagram very carefully. Now we will start from this side. Now you can see, and this is a rectangular type of a beam, and this beam is supported on two simple supports, and at the bottom of the beam section reinforcement is provided. And from the top we are applying some load, and when load is reaching the ultimate stage, ultimate load, you can see here some cracks are developed, which are just like inclined type of cracks from the bottom of the beam, and they are propagating towards the neutral axis. So this will be basically cracked section at ultimate stage, cracked section at ultimate stage. Now you can see here, and from this strain graph, strain in steel has reached, or you can say strain in steel is greater than strain in its yield strain. Basically this graph is for this is for steel, and strain in steel is more than strain which happen at yielding stage, and strain in concrete has reached its maximum limit as per IS code, which we have considered in assumptions part. So it is 0.0035. So you can see here some portion which is shaded here. This is effective portion of the beam section which is taking the compressive stresses, and steel is taking care of the tensile stresses. And accordingly, this stress graph you can see here, that stress at steel will be yielding stress of steel divided by partial safety factor for steel. And similarly, above the neutral axis, so this is the neutral axis, above the neutral axis you can see very clearly the stress graph is just like a non-linear type of curve, and this is the neutral axis. So this is the way how at the ultimate stage all these things happen, and how your beam section will be behaving, how cracks will develop. Now let us compare and try to understand all the three stages. The very first stage is uncracked concrete. You can see here some load is acting on the beam section. Steel is there, and the neutral axis is just looking just like at the mid of the section or towards the depth. So this is the neutral axis, and you can see here this much portion which is shaded. It is in taking care of the compressive, that is in compression zone. So accordingly, there will be the strain diagram as well as stress diagram. Now this is the case when whole of the section is taking care of all the stresses. It is uncracked section. Now next stage is cracked concrete, which we have discussed. When you are increasing the load, now even in this diagram you can compare. Here load is lesser, here the load has increased. Now when load has increased, what will happen? Some of the crack will start developing at the bottom of the section. Reinforcement is there. Now when this portion of the concrete is cracked, we will say that concrete is neglected at this zone for the calculation. Now if you compare this figure at the top and the figure, second figure, figure number 1 and figure number 2, effective area, shaded area of concrete which is taking compressive stresses has decreased comparatively. So area has decreased. Now it is a cracked section. Earlier, whole of the concrete section below the neutral axis was also taking the stresses, but now since it has cracked, and we will be ignoring the concrete below that. So that's why we are saying that in comparison to the figure number 1, that is of uncracked section, if you compare figure number 2, then neutral axis is getting somewhat seem to be shifting upward. So here you can say the stresses, strain in the steel at this level is less than the yielding strain. And similarly you can refer here, still it is a linear type of a relation in case of stress. So stress beyond above the neutral axis, it is compressive, and below the neutral axis we are not showing any stress here, because we have considered that below the neutral axis your section is concrete, whatever we, so stress is taken by concrete below the neutral axis are ignored. So that's why only steel is taking care of all the tensile stresses. And the third case which we have already discussed, now you can compare all these three stages. And in first stage load was lesser, in second stage load intensity has increased, in third stage load has reached its ultimate limit, and cracks have already propagated in the more area of the section. And you can compare figure 1 to 3. The effective area of concrete taking care of the compressive stresses has been considerably reduced, and now the concrete in the topmost fiber has reached its ultimate strain 0.0035, and here you can clearly see that strain in the steel level, strain in the steel is more than strain which is the yielding strain. And similarly, now this is the variation. Here we have considered the stress graph above the neutral axis, which is compressive stresses. So now it is a non-linear type of a diagram. So here I can create a second question, that why when we are switching over from cracked section to the ultimate stage, why the stress graph in the compression zone is taken as non-linear as compared to linear? So this is the second question, which the answer to which you can explore from the available resources of information, and just comment in the